Hello, and in this video we're going to be talking about exponential and logarithmic models. We're going to be dealing with half-life, doubling, and just any kind of growth rate. But let's take a look at a little bit of review first before we get into this. When we do this, we're going to be using two different models. And this was in a previous video, but here is this is our continuous model. And this is going to be our model that basically is going to be a rate at time 1 increment. Okay, so whatever our 1 increment is, it could be 1 year, 1 month. This will be the equation we use for that thing, and then this will be the rate at which happens at that one increment of time. So in this, we went over how to convert these back and forth. In these models, a sub 0 in this model is equal to little a in the other model. They're the same thing. A capital A here is the same as capital N in the models. Now, when we're doing this model, also e to the k is equal to b. So that means ln of b is equal to k. So these are the two equations we would use to find out what k is and what b is. We would do this. So if we knew what b is in this model, we can figure out what k is by just taking the natural log of it, and that'll give us this value up here in the equation. If we knew what the k was, if we knew what e to the k is, we can actually find this value of b in the other model. Now, most of the time I'll be using this continuous model because we're going to be modeling something that we're going to look at growing continuously or at any moment in time. But if they do ask you for like a yearly rate or whatever, we're going to be using this model then, because that's based upon 1 time increment. All right, so here is the section that we're going to cover. It's going to be dealing with half-life for the first example. It says we have this element that has a half-life of 3 days. The sample contains 100 milligrams initially. How much remains after a week? So what we have to do is, first of all, I'm going to use this formula that I put on the other page to figure out the growth rate, the continuous growth rate. That's what k is, a continuous growth rate. We're going to try to figure out what that is, what it grows at continuously. Now we know that it starts out at 100 initially. So first of all, we know that the equation is this because of the 100 milligrams. Initially, it's this equation. Now we're going to use this equation, and we know it has a half-life of 3 days. So we can plug that in and figure out what k is. So half-life means half of it's left over. So when we're dealing with half-life here, we know that it's 1/2 the amount is left after 3 days. So we can put the equation to be 50, because that's half of 100. Our initial amount is 100. Half of it's left over in 3 days, so we can put 3 in there. So this is our equation to figure out what our growth rate is. Okay, to solve that, we first take and divide by 100. So it's going to be 1/2 equals e to the 3k here. And then what we're going to do is we're just going to take the logable, natural log. Since it's e, I'm going to take the natural log of both sides. Natural log of 1/2 equals natural log of e to the 3k. And we have a rule that says that this is an inverse. Therefore, that's just going to be 3k equals ln of 1/2. So we're going to take that ln of 1/2 and divide it by 3 to get k. So k is equal to ln of 1/2 and then divided by 3. Okay, so let's figure out what k is using our calculator. It is all right, calculator. Natural log of 1/2 divided by 3 is negative 0.2. I'm going to carry this out to 4 decimal places. Negative 0.2310. 4 decimal places. Okay, so my equation then is going to be A equals 100 e to the negative 0.2310 times t. This is my equation for growing, or of the half-life of this thing. It's actually decaying or going down because it's negative here in the k value. If this was positive, then it would be growing at that rate continuously. We want to know what's going to happen after a week. So what we need to do is just use this now that we have the model. We can just plug in 7 days, because we did this in terms of days. So we can put in 7 right here and evaluate that. So we're just going to do that, take it and plug it into our calculator to find that value, and that would be 19.8, rounded to 1 decimal place, 19.85 milligrams would be there after a week. Okay, so we're using the same model. We're going to do that most of the time. I'm going to be using this model. Let's go to another example where we're going to use this model. This one does the opposite, which is saying it's doubling. So bacteria culture doubles every half an hour. If a sample contains 2,000 bacteria initially, what's size after 3 hours or after 80 minutes? Okay, well, we have to decide on a time increment. We have minutes and hours in here. So we can either make this up for minutes or we can make this up for hours. I'm going to, in this case, you can decide. It doesn't really matter. But I'm going to use, since we have a question about 80 minutes, I'm going to use minutes in my example. So my equation is going to be based upon minutes, not hours. So we're going to put this in there. We know initially it's 2,000, so we have this. As my equation. We know it doubles every half an hour, so that means it's going to be 4,000 in the matter of a half an hour. And in this case, a half an hour is going to be 30 minutes. We're going to deal with minutes here for time. Time in minutes. We're going to do that. Okay, we have to solve this to figure out my value for my equation, and then we can figure out what happens after 3 hours and 80 minutes after we have the equation. So we divide by 2,000. So we get 2 equals e to the 30k. All right, again, I'm going to use my natural logarithm thing. Take the natural log of both sides. We're going to get 30k because this is the inverse, so we're going to get natural log of 2 equals 30k. K is natural log of 2 divided by 30, which is approximately, this is growing, so it should be a positive k value. So natural log of 2 divided by 30 is 0.0231 to 4 decimal places. Okay, so that's what we have there. So my equation actually is, for this equation, it's going to be 2,000 is my initial value, e to the negative or positive 0.231 t. So this is my equation based upon minutes. T is in minutes. Okay, so that means that if we're going to ask what's the size after 3 hours, we would not put in 3. we would put in what do we put in here for 3 hours, since this is in minutes? So basically it would be 60 times 3, or 180 minutes. 60 times 3, 60 minutes in every hour. 60 times 3 would go in there. Now we just evaluate that, and that will tell us how many bacteria we have. 2000 e to the 0.20231 times 180. Okay, so in this case we have 127,887.0. So we want a whole number of bacteria. We can't have half of bacteria here, so we're going to round down to 127,887 bacteria in 3 hours. Now in 80 minutes we can just go back to the equation and plug 80 in, because it's in minutes. So in bacteria in 3 hours. Okay, and then our equation is going to be used again, but we're going to multiply that by 80 minutes this time. So we should have less bacteria, right? Instead of putting 180 in there, we're going to put in 80. We would then get 12694.2. So we're rounding to a whole bacteria again, so that would be we round down. So bacteria in 80 minutes. So this would be my answer. So 12,694 bacteria would be our answer for doubling, if we knew it doubled in every half an hour. Okay, so I'm using the same equation over and over again. We have an initial value that we're going to use, and we have a doubling or half time note, so that we can figure out what our growth rate is continuously. So we know what our growth rate is continuously based on that. Okay, so we may want to work our way backwards. So if we have to find a rate, what we're going to be doing is they're going to give us a day and an amount, and we're going to find the value of k for that value. So let's see. So in this problem, we start with 20 grams. After 7 days, the sample has 17 grams. That means it's decaying. That means your k value is going to be negative. We want to know what the half-life is, how long it takes to get to 10 grams. Okay, it's going to be longer than 7 days. But let's see if we can get this to work out. So I'm using my same equation. All right, but I want to know half-life. So I'm going to want to know, basically I'm going to want to know this equation. Eventually I'm going to do this. Half of it is left over, and I'm going to want to find time. So right now I have this 20 e to the we're going to have some number times t. So we need to find this. We need to find this growth rate, and that's what this sample 7 days is going to do for us. We're going to be able to find our growth rate or decay rate here in this, and plug it in here and solve for t to figure out the half-life. So this is the question I'm really going to want to solve, but I don't know my growth rate yet. So I'm going to use my initial value and another value, 7 days is 17 grams, to help find my rate, just like I did before. So I know we know that 17 would go here because that's how much we have, and we know it's 20 to start with. We don't know the growth rate, but we know that it took 7 days. So this equation filled out except for our continuous growth rate. We know how much it started with, we know how much it has. So we're going to take this equation and solve for k. So when we're doing so, that's going to give us our continuous growth rate that we're going to use over here to help us find our time for half-life. Okay, so we do the same thing as we did in the previous ones. We divide by this number here so that we can get e by itself. So if we do that, we get 0.85. 0.85 equals e to the 7k. K times 7k. We're going to take the natural log of this to basically, we're using that to undo this operation because we know that that's an inverse, and we have a property that says if we use the inverse here, we just get this. So 7k is going to equal ln of 0.85, and we're going to divide by 7 to get k. So ln of 0.85 divided by 7 equals k. So in this case, our answer is going to be, for k, negative 0.0232 if we're rounding to 4 decimal places. All right, so we have that up here. Now we know what to put here, negative 0.0232 t. So we have that equation. We can solve that now. First step, again, we want to divide by this 20, just like we did in every other one. We divide by the number in front of e. So we're going to get 0.5, because that's a half-life, e to the negative 0.0232 t. We're going to do the natural logarithm on both sides again, so we can get rid of this e. So natural logarithm of 0.5 equals natural logarithm of e to the negative 0.0232 t. These are going to go away, and you're going to get negative 0.0232 t equals ln of 0.5. And if we divide that, we should get our half-life in days. So we're going to divide these numbers, 0, 2, 3, 2, and we'll get the time increment here. So using my calculator, I get 29.88 days. So this time increment is 29.88 to 2 decimal place, and that would be in days. So 29.88 days would be when it's the half-life of that. Almost 30 days would be its half-life. So it would take that long before half of it's left over. Okay, here's my second example of a similar type of question. We're going to go, this one's a little bit different because it doesn't give me an initial value. It says we have a culture that grows from 600 after 20 minutes. So we don't know what it happens at the initial value. We know what it happens after 20 minutes, and we know what happens after 35 minutes. It's grown to 2,000. We want to find our growth equation, our doubling time, what's the population after 100 minutes, and when will it reach 11,000 in the culture? When would the population reach 11,000? So we're going to try to answer all those questions. So in this one, it's a little bit difficult because we don't have our a sub 0. In our every other previous example, we had a sub 0. We had this value, so that made it easy. So in this one, we're not going to have a sub 0. We're going to have to write both of our equations without a sub 0. So we're going to have, we know we have 600 in our first one, and that's going to take 20 minutes to do that. So we have that equation. And our other equation is going to be 2,000 equals a sub 0 e to the 35, or k times 35. So basically we have these two equations, and we have two unknowns. We have the initial amount we don't know and the growth rate we don't know. So we're going to have to take one of these two equations and substitute it into the other. Now what might be easier to do than doing that would be just to divide these two equations. That might, because they have the exact same things here on this side. So if we divide them, we should be able to divide both sides. If we know they're equal and we're dividing 2,000 by 600, and we know this side is 600, so we're going to, and this side's 2,000, so it's 2,000 divided by 600. So if we divide these two, we know the order of the exponent property in division is just to subtract the exponents, right? So this might be easier just to divide. If we just take the little larger value and write it as 35k here, and the smaller value, write it as 20k, and we divide these two, because we know this side divided will be the same as that side divided. So we're still going to have an equal equation, because this is 2,000 here, and when we divide 2,000 by 600, we're going to get the same value on this side as we would on this side. So reducing this, I'm not going to use my calculator yet. So reducing this, we got 20 over 6. That's going to be 10 over 3. We're going to leave it that way, reduced. Now when we divide a sub 0 by a sub 0, they reduce to 1. So this whole factor reduces to 1. And when we divide the e sub e with the power, we subtract the power. So this part of it right here, this part of it is we're going to subtract the power. So it's e to the 35k minus 20k. And we can actually do that. So we got 10/3 equals e to the 15k. So now we don't have a sub 0 because when we divided it, it reduced down to 1. We got rid of that. Now we can just solve this equation, and that should give us the growth rate. So this is another method. Some of the methods we've used in the past is we solve for a here. We may solve for a and then do 600 divided by e to the 20k is going to be a sub 0. And then we substitute it in here. All right, and when we do that, we're going to get the same answer as this. Eventually, we're going to get down to this equation. So I did a little shortcut here by knowing that when we divide both sides, since both sides are 2,000 here and both of these sides are 600, we're going to get the same thing on both sides of the equation when we divide. So we're going to take the natural log. Going back to this, we're going to take the natural log of both sides here because we know we want to get rid of the e. It's on this side. And we know that these are inverses, so that's just going to be 15k equals natural log of 10/3. And we just need to divide by 15 to get our answer here. Reduce this down. And this is going to be our answer for k. And that would be, typing it into my calculator, k is going to be 0.0803 rounded to 4 decimal places. So now that I have that, we have an equation. I don't know what a sub 0, I don't quite actually have the equation yet because we need to find out what a sub 0 is when we do the division. But since I solved this one up here for a sub 0 using my old method, we can then plug it back in. Or you can take this number and plug it back in right here and find a sub 0. So I'm going to take my 600 equation, which was 600 equals a sub 0 e to the 20k, and I'm going to put in the k value of 0.0803. And so I'm going to figure out what this is. So I'm going to take my calculator, I'm going to compute this value, and then we're going to divide by that. So that value is 4.0 4.98 to 4.98, 4.9828. If we're going to 4 decimal places. That went a little off the rack. 28. And times a sub 0 equals 600. So I'm just going to divide by that thing, this number, and to get a sub 0. A sub 0 is 600 divided by 4.9828. So I get 120.4. I'm going to round to one place here. Okay, because it's bacteria and you can't have, it's growing, the population, it's probably not going to have a decimal in most cases, so we're only going to keep one decimal place here for that part. So my equation basically is going to be A equals 120.4 e to the 0.0803 t. This is my growth equation. My initial value is 120. I'm going to round down 120 bacteria, or whatever this is. Doesn't say what it is. Let's see, we need to find our doubling time and how much it's going to happen in 100 minutes. So let's see, we have answered this question. We want a doubling time, so we want to double this. So in doubling this, it's 240.8 equals 120.4 e to the 0.0803 t. We're solving this. This is our doubling time equation, because we doubled it. We doubled the 120.4 and put it here. So I divide. I'm going to get 2 equals e to the 0.0803 t. Take the natural log. That's going to get rid of this and just give me the exponent, and I divide those two numbers, and I get 8.6. So we're going to say our doubling time is 8.6 minutes. Okay. So our doubling time is 8.63 minutes. 8.63 minutes is our doubling time. Okay, our other questions here are what's the population after 100 minutes? Okay, so that's a simple plugging in 100. So A equals 120.4 e to the 0.803 times 100. We can just get that answer out of our calculator. I get 3,698.37 and a 0.6. I'm going to just round to this many bacteria of the culture. It's a whole number thing. There's 369,837 in the population after 100 minutes. Now, when does it reach 11,000? That would be solving the equation in the reverse fashion. So we put 11,000 equals 120.4 e to the 0.0803 times t, and we find out what the answer is. So we're going to divide that by 120.4, And then we get 11, let's see, we get 91.36, rounded to 2 decimal places. And we're going to want to take the natural log. That's going to get rid of this e and give us a decimal, just the exponent because they're inverses. And we need to solve that. So natural log of 91.36 divided by 0.0803 gives me 56.2. So 56.2 minutes. To reach 11,000. In population. Okay, so that's my answer for that question. Okay, now moving on to another example that uses an equation called the Newton's law of cooling, where we have two different temperatures. We have a temperature of an object and a temperature of the air around it. We still use this same equation we've been using, but we have to subtract the temperatures before we use that process. So I have an example of this. We have water sitting out. We've heated the water up to 190 degrees Fahrenheit, and it's now, we took this out of the heat, off the heat, and it's now sitting in a room that's 70 degrees. And it knows if the temperature is 170 after half an hour, that means it went down 20 degrees. What will the temperature be after 70 minutes? How long does it take to cool to 110? We're going to use this equation to do that. The only difference between this equation and one we're using is we have this additional temperature of the surrounding air in it. I have this equation, or this example of this process. So let's take a look at this. We have water at 190 degrees Fahrenheit. It's cooling in a 70 degree Fahrenheit room. The temperature is 170 after a half an hour. What will the temperature be after 70 minutes? How long will it take to cool to 110? So we're going to use the initial value in here to help us find the initial constant. The initial constant is something that's found using the initial value. So initially it starts out of 190 degrees, right? So we're going to take our initial value here, which is 190, and then that's going to be when time equals 0, and we have everything else in the equation that we're going to need to help us find A. So we have 190 is our initial value. We don't know what A is. That's our initial constant. E to the k times 0, because that's time is 0. And we know what the temperature of the room is. It's 70. So we're going to use this to help us find out what A is. So this part of the equation right here, this part of the equation we can evaluate. This is e to the 0. Anything to 0 is 1. So this is A times 1 basically, plus 70 equals 190. So A is going to be 120. It's 70 from 90, 190. So that's our A value. So that means my equation now is T sub T equals 120 e to the k times t plus 70. So we have this equation now. We need to figure out what k is. So we're going to use this the next temperature that we have, the 170, to figure out what k is, the rate. So we know 170 goes here. That's how much the temperature has risen to. We know what time is. And since we're going to want to know 70 minutes, we're going to use minutes here instead of hours. So we're going to put in 30 here instead of 0.5 so that we're in minutes. So we're timing in minutes instead of hours. Okay, so we're going to solve this. So the first thing I do is subtract 70. I get rid of the 70. I subtract the 70 off the side. I subtract 70 from here. I then get this equation, 30K. So I get this equation. I then divide by 120. Okay, I'm going to leave that as a fraction. That's 10 over 12. That's going to be 5 over 6 equals e to the 30k. So I'm going to then need to take the natural log and divide. When we take the natural log, it gets rid of the e on that side. So we're going to do that. And I get k equals negative 0.0061. So now I have the k value. I'm going to put in the equation completely. So now I know my equation is t sub t equals 120 e to the negative 0.0061 t plus 70. Now if I want to put in 70 minutes, I'm just going to evaluate this with a calculator. To get the answer. So if we just plug that into our calculator, we should get a value. So I get t sub 70 as being 148.3. So that's telling us after 70 minutes the temperature in the thing will be 148 degrees Fahrenheit after 100 or 70 minutes. After 70 minutes. So that's that problem or that solution to the first question here. What is the temperature after 70 minutes? And then it asks how long does it take to get 110? So that's solving the equation backwards. So we started with 110 being our temperature, and we're solving for t. So the first thing we do is subtract 70 from 110, and then we're going to divide by 120. So if we do that, we get 40 equals 120 e to the negative 0.0061 t, and we divide by 120. And we reduce, 4 goes to 12 1/3, so it's 1/3 equals e to the negative 0.0061 t. We take the natural log of both sides. When we take the natural log of this, the e goes away. It's the inverse. So we get the exponent, and then we just divide those two together. And we get 180.1 for t. So t equals 180.1, and that's how much time it took to make it to 110 degrees. So after 180 minutes. It would reach the temperature of 110 degrees for this water as it cools. Okay. Now, the last thing we're going to do here is a logarithmic scale. This application is just a number line application. It's pretty simple in that they draw a scale. They're going to put the number line here on the scale. They're going to say, okay, here's 1, 2, 3, and -1, -2, -3. And they're going to put a number, a point on here. So maybe somewhere like halfway in between this. And they're going to say, this is the log of x. Now this is base 10. So what we would do is we would say the log of x equals, by this picture, -1.5. So to figure out what x is, we just convert. This is base 10, so it's 10 to the exponent, -1.5 equals x. So we're just converting it into the other form. And so our answer to this problem is approximately, for this answer, x is approximately 0.316 to 4 decimal places. So this is the exact answer, but this is the decimal answer. They're going to give you a graph in the problem, and they're going to do something like this, put it halfway in between. You just need to write the equation based upon what they told you here. If it says ln here, then we're going to use base e to that power. But if it says log, then you're going to use base 10.